Oh, all right, it is Friday, it is the 5th, and we're doing the integral test for testing for convergence of series with all positive terms. Okay, so what does that mean? Well, let's see. What if, okay, what if I gave you this series? Where's my pointer? There it is. Kindly consider the following series. Now, usually, what we did yesterday was rare. With geometric series, not only did we figure out when it converged, but what it converges to. That's a rare result. Very often you can't tell exactly what it converges to. But usually all you need to know for power series next week, well, next unit, all you need to know is whether we converge or not. Okay, so here's a test for convergence when you're not too sure. Let's say I have this series. The sum as k goes from 2 to infinity of 1 over k ln k squared. Now this is some wild series. I don't know anything about it. It's not harmonic. It's not geometric. What the heck is it? I don't know. Plug in some numbers. Maybe you can see a pattern. Let's see. Plug in what first? 2 in for what? Okay, notice we don't always have to start at 0 or 1. It doesn't always have to be n, right? Okay, don't get crazy. 1 over 2 ln 2 squared. Plus, what's the next term? 1 over 3 ln 3 squared. Plus, 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 plus. Okay. Does it pass Cauchy's divergence test? Are the terms getting smaller and smaller and smaller? Yes, they are. Okay. By the way, it's not only known as the Snowball's chance in hell theorem, it's also known as Cauchy's minimal criterion for the convergence of series with all positive terms. Holy cow, that's one long name. Okay, so Cauchy's minimal criterion for convergence is passed, but we still don't know if it converges or not. It has a chance of convergence, right? But it may not. Okay, well here's an idea. What if we find something whose sum is bigger than that, and we show that it converges? If we can figure out something, the numbers of which we add up, they end up being bigger than this number, whatever we get if you add this up forever, then if this is smaller, this converges too. If the other sum converges and it's bigger, right? Well, it can be shown that the improper integral that you get by converting this to a function. Are you ready? 1 over x ln x squared. I can't write. 1 over x ln x squared dx, right? What did I do? I took the discrete variable k and replaced it with the continuous variable x. And now I make it an improper integral from 2 to infinity. It can be shown that this area, if it converges, this area is larger than this. So if this converges, that converges. If this diverges, this area is actually smaller than this. If this diverges, that diverges. Okay? So if this converges, that converges, that diverges, that diverges. That's convenient. Can you do this using improper integrals? How do you rewrite this? Who's bad, A, B, or C? B. The limit as b goes wild. Okay, the integral from 2 to b of 1 over x ln x squared dx. Well, then, wait a minute. Can you integrate that? Is it partial fractions? I'm not sure about that. Yes? Yeah, if u is ln, du is 1 over x dx, isn't it? So I'm going to write it this way. The limit, as b goes wild, the integral from 2 to b, of ln x to the negative 2 dx over x. So if you make this u, this is du, right? So how do you integrate u to the negative 2 du? Right? It's a power rule, in other words, right? How do you integrate u to the negative 2 du? You get u to the negative 1 over negative 1. Okay, good. So let's say that's the limit as b goes to infinity of, let's see, ln to the negative 1 over negative 1 is negative 1 over ln, isn't it? Evaluated from 2 to b. All right. So let's do that. The limit as b goes to infinity of negative 1 over ln b minus a negative 1 is a plus 1 over ln 2. All right, so does that limit exist? If it exists, so does the series converge. If the improper integral does not exist, so does the series diverge. So, what did say you? Okay, don't be like algebra 2 and trig, huh? Is it convergent? What do you think? Spencer, you were saying what?
Yeah.
Why?
Because 1 over ln b, that goes to 0.
Right, so what's the limit? 1 over ln 2. Right, okay. Now remember, if this limit exists, it's not this sum. Okay, don't confuse the two. But it's bigger. I can show, this can be shown. I'm not going to prove this theorem. This is a theorem. The integral test theorem can be proven. I'm not going to prove it. We don't do that in this course. But if this converges to a number, in this case, what was it, 1 over ln 2? Whatever that number is, it's bigger than whatever this is. Okay? It's not the same as this, but it's bigger than this. So if that exists, so does this. Okay, so we're going to say, therefore, hey, look, give me the thing. Okay, this is what you say. They like to see this on the AP. Therefore, the series, as k goes from 2 to infinity, of 1 over k ln k squared converges by integral test. You don't have to say much, but you got to say something. Okay? That's it. That's the integral test. So that's why we needed improper integrals, okay? All right. What about, let's see. Let's try another one. Are you ready? Is that okay? Any questions on that one? Problems with that one? No? Yes? Maybe? We're good? All right. So you got to know your u subs. You got to know your integrations. You might need some partial fractions. You might need some by parts. You need improper integrals. All of that stuff comes into play. All right. How about this one? Well, we saw this one yesterday. Let's see if we can prove it by harmonic, that the harmonic diverges. Remember the harmonic? We know that it diverges, right? Let's see if the integral test says that. Well, remember what this is. This is 1 plus a half plus a third plus a fourth, right? We already showed this diverges yesterday, right? Let's see what the integral test says. Let's see how it works when there's divergence. How do you rewrite a discrete function in n as a continuous function that you can integrate? You replace a discrete function with a discrete variable n with x. So it's just 1 over x dx, the integral from 1 to infinity, right? Again, this is a, b, or c. b, the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. All right, good. What's the antiderivative? It's ln, right? Okay, so this equals the limit as b goes to infinity of the ln of x evaluated from 1 to b. Okay, fine. Limit as b goes to infinity, ln b, absolute value of b, minus ln absolute 1. This is 0. What happens in the limit? Diverges, right? This limit does not exist. Okay? Therefore, this series diverges. I can't write. Diverges by integral test. All right, now I'm simplifying things here. There's a number of things you have to check before you can apply the integral test, okay? This is the guts of it. If you get this, you got the integral test. But be careful. There are 3 antecedents to the integral test theorem. What is an antecedent? When you write a theorem, you usually write if stuff, then stuff. I didn't tell you the if stuff. If stuff, then you can do the integral test. And if the improper integral diverges, so does the series. If the improper integral converges, so does the series. But what's the if stuff? The if stuff, you got to be careful. It has to pass Cauchy. Okay? So the limit as 1 over n, of 1 over n as n goes to infinity must be 0. Okay? And aside from that, how am I going to say it? The function that you get, its derivative must always be negative. In other words, it must be decreasing. The numbers you're talking about must be decreasing towards 0, not just as limit of 0, but decreasing towards 0. What's the function we're dealing with? F of x is 1 over x. What's f prime? What's f prime? Derivative, go for it. It's negative 1 over x squared, right, exactly, okay. Is this always negative on this domain? Yeah. So f prime is negative for all x from 1 to infinity. And is f of x continuous on this domain? Otherwise you can't integrate. Or you can break it up as more improper integrals, but that's a mess. All right, so there are 3 antecedents, 3 thens that you have to worry about. Sorry, ifs. If it's continuous, if it's decreasing, if it goes to 0, then apply the integral test. And if you apply the integral test and you get a number, whatever that number is, it's bigger than this, so this converges. If you do the integral test and you don't get a number, this diverged, so did this. Okay? You have to do these 3 things. Yeah. Well, actually, I sort of did it backwards. F of x must be continuous. Okay? F prime must be negative. And you can do this in terms of x if you want. Might as well just do everything in x. And the limit as x goes to infinity must be 0. Okay? So the first thing you do is you convert this to a function in x, and you test. Is it continuous on this domain? Yes. Is it decreasing for all x on this domain? Yes. Is the limit as x goes to infinity 0? Yes. Then this stuff we did applies. Otherwise, it does not apply. Okay? Yes, sorry, I made a little mess here. Whoops, I got a little messy. Okay, let's try that again. Are you ready to move ahead? Everyone okay? All right, look, I'll make this a little more clear on the next example, okay? Here's the next example. What if I did this? That's an infinity, okay? First thing you do is you rewrite this as a function in x, so what do you get? 1 over x squared. Okay, so 1. Is f of x equal to 1 over x squared continuous for all x from 1 to infinity? Yes. 2. Is f prime of x always negative? In other words, is f decreasing on this domain? Well, what's f of, if that's f, what's f prime? That's x to the negative 2, so you get negative 2, x to the negative 3. In other words, negative 2 over x cubed. Now, all the x's here are positive, right? So this denominator is always positive. This numerator is always negative. That's a constant. So yeah, right? And 3, 3, we said the limit as x goes to infinity of this function we made up, is it 0? Yeah, so if you have to state this before you start the integral, okay? If all 3 antecedents of the integral test theorem have been met, then write the improper integral. What is it? The integral from 1 to infinity of 1 over x squared dx. Okay, so can you integrate that thing? What kind of integration can you do? Okay, the limit as b goes to infinity, the integral from 1 to b of 1 over x squared dx. And how do you anti-differentiate? What rule are you going to use? X to the negative 2 and others power rule. Yeah, okay, might as well just write it that way. X to the negative 2 dx anti-differentiates how? X to the, what? What happens? I didn't hear it. X to the? Negative 1 over negative 1, right. Okay, so in other words, negative 1 over x, isn't it? Okay, so that equals the limit as b goes large of that mess evaluated from 1 to b. So let's see that. Let's see the limit as b goes to infinity of negative 1 over b minus minus is plus 1 over 1. Does that limit exist? Name it. If this limit exists, so does this. This, by the way, is a limit of the partial sums, right? The limit of the sequence of partial sums is the sum of the series. All right, so, but does this, the fact that this adds up to 1, the fact that this adds up to 1, does that mean that this adds up to 1? No. In fact, this is a famous result. This is called Euler's series. He figured out that it's exactly pi squared over 6. How he did it is lost to antiquity, because he did it without calculus, and he did it without how. How the hell did he do it? Nobody knows. But it has since been proven to be exactly correct. Lucky son of a gun, I guess, yeah. All right, anyway, this is called Euler's series. In fact, it's the basis of the Riemann hypothesis, for which there is a $1 million prize. Look it up. If you can prove the Riemann hypothesis, you got $1 million. What's the Riemann hypothesis? That if n is allowed to be, if this exponent is allowed to be complex, that there's a formula for a convergence, no matter what number you pick here. Now there is a formula, you can look it up on the internet if you like. If this is an even number, right? If this is an even power, there's a formula for this. They all, like, if this is 3, it's pi cubed over something, 27, I don't know, something weird. If it's to the 4th, it's pi to the 4th over something. If it's to the 6th, pi to the 6th over something. The odds, there's no formula. Nobody knows it. Complex, Riemann came with some kind of a conjecture. It hasn't been proven. If you can prove it, you get $1 million. Why? Because it can be used to find very large prime numbers. The Riemann hypothesis is a gold mine. It's also destroyed many mathematicians. They've gone insane trying to solve it. All right, anyhow, but that's a digression. So, if this converges, it's bigger than this, so it converges 2. By the way, this is not 1, is it? So let's not worry about that. Okay, does this sound familiar? Didn't we do p integrals? Isn't that a p integral? Right? When we go from 1 to infinity and p is greater than 1, we get 1 over p minus 1. If p is 2, we get 1. Remember this? We did this already. Okay, so next. How about this one? What if, so wait, let me back up for 1 second. So if this is a p integral, guess what this is called? A p series. So when p series, the series always going from 1 to infinity, right? This we did from 1 to infinity. We also did it from 0 to 1, right? We're only interested from 1 to infinity. All of these converge when p is greater than 1. All of these diverge when p is less than 1. For example, look at this one. Is this a p series? Is that a p series? If so, what's p? A half, right? Okay, 1 over n to the p. P is 1/2. Okay, so if this is a p series, can you use a p integral to find whether it converges or not? Let's see. First, what's the antecedents of the integral test? 1. What's the function we're dealing with? 1 over what? Rad x. Okay, is this continuous for all x from 1 to infinity? Yeah, the only problem would be 0. That's not in here. Okay. 2. Is f prime always negative? Well, what's f prime? Well, this is x to the negative 1/2, so what do you get? Negative 1/2 x to the negative 3/2, which is negative 1 over 2, the cube root of x squared. No, I said it wrong. The square root of x cubed. The square root of x cubed. Now, remember, these n's and these x's are all positive, right? So the denominator is going to be what? Positive, but the numerator is stuck. It's a constant, and it's always negative, so this whole thing is negative. F prime is negative. The function is decreasing. So if the function is decreasing, and it's continuous, and the limit as x goes to infinity of this function is 0, you're in business. And is that true? Does that go to 0 as x goes crazy? Yes, it is. All right, so those are the three antecedents, or the antecedent, of the integral test. So let's do the integral test. The integral from 1 to infinity of 1 over rad x dx. But again, is that an a, b, or c? That's a b. And again, what rule are you going to use? Our rule, x to the negative 1/2, right? Okay. So how do you anti-differentiate this? Remember, we differentiated it before, right? We're not doing that. We're anti-differentiating it now. So what do you get? X to the 1/2 divided by 1/2, or times 2. Okay. So isn't that just rad x? I'm going to write it that way. So you get the limit as b goes wild of 2 rad b minus 2 rad 1. Well, that's 2 times 1 is 2. All right, so tell me, does this limit exist? If so, name it. Does not. Right? Rad b gets humongous as b gets humongous. Okay. So, what's your therefore statement? You got to have it. You don't have to use this. You can write therefore, okay? Therefore what? This series, as n goes 1 to infinity, of 1 over rad n, what? Diverges by integral test. That's all. They get really pesky about these questions on the free response. All right, so if this is a free response question, you got to show this, right? You got to show this. You got to show this, okay? All righty? So, questions. So guess what? Now we have infinitely many p series we know to converge and diverge. When p is, why did this diverge? Because p was what? Less than 1, right. Well, it's always positive. So between 0 and 1, right. Less than 1. So a p series where p is less than 1 diverges. And a p series where p is greater than 1 converges. And that's all you need to know about p series. That's what we did p integrals. Isn't that nice? Okay. Okay, questions? Are we okay with this? All righty. Then, how about, yes? When, right, less than or, equal to, no, remember we proved by integral test that when we had a 1, it diverged. In fact, that was the harmonic series. We just saw that. When we did the harmonic series with the improper integrals just now, it diverged. That's a p equal 1. 1 over n to the 1, that's harmonic, that diverges. Yeah, look. We just did it, look. We did it without saying that it was a p series. This one, when p is 1. Think of this as a p series where p is 1. That's the harmonic. We showed that the harmonic diverged yesterday, and we proved that the harmonic diverged today by integral test. So when p equals 1, p series diverge. Oh, I thought you said, okay, say what you said again.
I said when p is less than or equal.
It will diverge. Yes, okay, you're right. I'm sorry. I thought you were saying something else. Okay. Yeah, the point is if it's greater than 1, it converges. Okay? That's all you need to remember. Okay. Now, this is not a p series. Let's see what you can do with this. This was an actual free response question. They give you a series like this. And they ask you whether it converges or not. That's it. They don't give you sigma, they don't give you nothing else. Does that series converge or not? 1 over e, 2 over e to the 4th. Whoops, I messed up. 3 over e to the 9th. Sorry. Well, first, can you write that as a sigma? How would you write that as a sigma? Can you? If n starts at 1 and goes to infinity, okay, what? N over e to the n. Perfect. That's it. That's fine. Great. All right. So now, can we use the integral test on this? Oh, did you say n squared? Whoops. He messed me up. See what he did? Yeah, it's n squared, right? Because when this is 1, that's 1. When this is 2, that's 4. When this is 3, that's 9. Yeah. Okay. Good. Thank you. Which, yeah, it better be because otherwise you can't integrate that. All right. I'm trying to use the integral test here. All right. So what's the first antecedent of the integral test? Let's see if we can use it here. First we have to name the function. What is it? What the freak is that? What was that? Okay. It's x over e to the x squared, right? Okay, now, is that continuous for all x from 1 to infinity? Right? There's no weird radicals with a negative, no zero denominators, nothing weird going on. Okay, so it is continuous. 2. What's f prime, and is it always negative? Well, how do you take the derivative of that thing? Low, d high, minus high, d low. Whoops, d low. Now, how do you do d low? The derivative of e to the u is e to the u du. All over low, low. Well, by virtue of the fact that I said low, low, this is something squared. Something squared is always positive. So the denominator is always positive. Is the numerator always negative? That's what I want. I want this to be negative. Yeah, I don't know. Let's see. This is e to the x squared. This is e to the x squared. I can factor it out. Okay, e to the x squared times 1 minus 2x squared. Is that right? Over e to the x squared squared. Is it cubed? Why? Why? X times x. Are you okay with that? I think so. All right, so on this domain from 1 to infinity, isn't this always subtracting something bigger than 1? Isn't this always going to be negative? This is always positive, by the way. Right? It has a horizontal asymptote of the x-axis, always above the x-axis. This is always positive, this is always positive. This is always negative. So we're good. So continuous, negative derivative, and what's the last part? The limit as x goes to infinity of this crazy thing. Now what was it? It was x over e to the x squared, I guess? Okay? What is that limit? That's a tough question. Have we talked about this? Is this top heavy, bottom heavy, or equal degree? That would be nice to know. Because it's rational, right? If it was top heavy, it would go to infinity. If it was bottom heavy, it would go to 0. If it was equal degree, it would go to the leading coefficients, or L'Hopital. It's bottom heavy. How do you know? Did we talk about this? Yeah, well, I mean, look at the terms. The denominators are growing really incredibly fast. The numerators, yes, we're growing a little bit. Right? So it looks like it's bottom heavy, right? Here's a quick acronym. Remember Long Island Pet? I don't use acronyms a lot, but there's 2 acronyms I use in this class. Long Island Pet, a good choice for you by parts, right? Did I tell you this one? NN-FEPL. Did I mention this yet? It's a real catchy tune. I don't know the tune. There's a song for this. NN-FEPL constant, okay? For n large enough, n to the n grows faster than n factorial, that's factorial, then 2 to the n, that's exponential, then n squared, that's polynomial or power, then log n, that's logarithmic, then any freaking constant, because it's not growing. Okay? So what do we got here? We got poly, and we got exponential. Which one grows faster according to this table? The higher up you are, the faster you grow. Exponential grows faster than poly for n sufficiently large. Well, guess what? It's going to get as large as you want. So it is bottom heavy. So this is 0. Okay? This can be proven. I'm not going to prove this. By the way, notice, this is a power function because the variable is in the base. This is an exponential function because the variable is in the exponent. This is, I don't know what the hell to call it, but it's both. So that's why it grows insane. There's no name for this, but it grows insane, and it comes up in series a lot. So keep it in mind. X to the x, I don't know what the freak that is, but it grows really fast. Okay. So can we apply the integral test to this series? Yes, we can. And we're going to use this function. Okay, good. So the integral from 1 to infinity of this thing, right? Oh boy, this is getting long. The integral from 1 to infinity of x over e to the x squared dx. Good. Now, how do you anti-differentiate that? And of course, you know it's a, b, or c, right? Is it a, b, or c? These are all b's, right? Because it's going to infinity all the time. So the limit as b goes to infinity of the integral from 1 to b of, well, what if I write it this way? Does that make it easier? Yusuf, who's u? Negative x squared, right. If u is negative x squared, du is negative 2x dx, I've got x dx, so I'm going to replace it with negative 1/2 of du. So it's negative 1/2 e to the u du. You're going to use the e to the u rule. How do you integrate e to the u du? It's e to the u. Duh. Okay, so limit as b goes to infinity of negative 1/2 e to the u. Right? Okay, and we're evaluating that from 1 to b. So let's do so. So that's the limit as b goes to infinity. Now, this negative exponent really means that these humongous powers are in the denominator, right? I'm going to write it that way. That might make it easier to evaluate the limit. Negative 1 over 2e to the b squared. Minus minus is plus, plug in 1 into here, and you get 1, what do you get? You get 1 over 2e to the 1, negative 1. No, I got rid of the negative, I'm sorry. 1 squared is, well, 1. Done. That's it. All right, so does this limit exist? And if so, name it. It's 1 over 2e, right? Because e to the b squared grows really huge, really fast as b goes to infinity. And if that's in the denominator, this becomes indistinguishable from 0. This limit is 0, so we get 1 over 2e. Okay? So if this converges, if the improper integral converges, so did the series we started with converge by the integral test. So let's say so. Therefore, the series, as n goes 1 to infinity, of n over e to the n squared converges by integral test. Now, I have no idea what it converges to. It converges because this exists, but it doesn't converge to this. What does it converge to? Let's find out. Let's see if it in fact converges by looking at a graph on HAL. How about that? Okay, let's graph HAL. Graph stuff on HAL. Whoops, I'm in ludicrous speed, it looks like. Okay. And go into mode. Am I in sequence mode? No, let's go to sequence mode. Let's go to y equals. All right, and it's going to be, now I want to do the partial sums, right? So alpha u1 of alpha n, mine got erased from yesterday, minus 1, plus, what are the terms? Well, it was n over e to the n squared. Okay, so it's alpha n divided by e to the n, alpha n, where's n again, squared. Boom. All right, that's the series, right? Now, what's the first term? Well, let's see, they gave us the first term, didn't they? There it is. Okay, so let's plug that in, because it's adding the previous sum to the current term, but it doesn't know the very first one to start at, right? So let's write 1 divided by e, or, cut to the chase. It's e to the negative 1. Okay. What about the window? Well, first 10 terms, I guess that's okay, but I don't know if I like this here. I'm going to make this 0. I don't know how big it gets, so I'll leave the x max, y max, all that stuff alone. Let's graph it. Oh, what I did this backwards. Whoops, sorry. What did I do? I did stupid. I meant to do 0 here and 10 here. Sorry. Well, it's growing, but very slowly, huh? Doesn't look like it's growing by much. Let's make the window go to 100 or something. Does it look like it's going to a horizontal asymptote? Yeah, it's way small. I think my y max of 1 would be enough, really. It's horizontal. I mean, come on. That's convergent. Holy Moses. That's about as good as it gets. Yours overflowed?
Yeah, it just said over.
That's odd. Well, e to the 100 squared is going to be pretty damn big. It depends on your operating system how that is handled. If it figures that out first, or if it divides it first or something, that's going to... Really? All right, wait. Now, let's see. What if I make the window, I don't know, y max? I don't have any negative y's. How about a y max of 1? That's probably enough. Look at that. Oh, I'm getting an overflow, huh? Huh. Well, it's over infinity, that basically. That's why it's not adding anything. That's why it's flat. All right. What if we did a convergence table out of this? Alpha U1 of 1 is the first term. Apparently that's 1 over E. And then the first 10 terms. And then the first 100 terms. And it's working hard. And there you go. Done. I'm done. I got 6-place convergence. I can state that with accuracy to 5 places. And so the series exists. Yeah. Why can't I what? You can. I just prefer this. I like to see it graphically. You could use this, you could convert it to a function in X and use sigma in function mode if you want, but that's complicated. We will do that when we do power series, because power series adds x's to this, and we're going to need the function mode and sigma there. We'll do that. All right, so I'm approaching it slightly different here just for fun. All right, so how are we doing on time? We're about out of time? We got a couple minutes? All right, you know what? I'm going to stop it there, because I got one example here that's insane that I don't know if it's going to help or not help, so leave it there. All right, I'm done. Bye-bye.